El Nino and the Arctic Oscillation are two teleconnections. And now I want to mention a couple other ones. These are climatic variations that are short-lived. And the teleconnections, remember, are just changes in pressure between one place and another. And they drive climatic variations over many different parts of the Earth. The North Atlantic Oscillation is one that affects the East Coast quite a bit. You can see that in this picture here. We won't go into the details of that one since we are on the West Coast. So we're more interested in the Pacific Decadal Oscillation, which actually has the biggest influence on the Pacific Northwest weather. So Pacific Decadal Oscillation, it has a warm phase and a cool phase, or a positive phase and a negative phase. Here's the warm phase. It's not warm over the whole area, it's warm along the west coast of the United States. And the cool phase or negative phase is cool along the west coast. So the Pacific Decadal Oscillation, also known as the PDO, is a major interdecadal climate variable in the Pacific Northwest. Interdecadal, in other words, between decades, so many years, not like the El Nino and La Nina, which are just a few years apart. This would take place over 2 or 3 decades or something like that. Typically lasting for 20 to 30 years. The warm phase and the cool phase. This is the warm phase here, this is the cool phase here. These are shown here with the typical wintertime sea surface temperatures in the colors that you see. This is a temperature anomaly again. We've been talking about anomalies, so 0 would be normal. And then this is in degrees C, so warmer in red colors and cooler in blue colors. This is also a seesaw, and you're getting PDO index. And this is from 1900 to 2008, and you'll see that it's varying over a long period of time. Notice that each of these blocks is a decade, so this is about 2.5 decades. Here's about 3.5 decades, about almost 3 decades here. So Pacific Decadal Oscillation. Warm phase is positive here, and the cold phase is negative. Now, the interesting thing about this Pacific Decadal Oscillation is it also not only influences our weather, it also influences fisheries. So the Northeast Pacific marine ecosystem, okay, Northeast would be in the Pacific Ocean, so that would be our northwest coast. That ecosystem is going to be changed by the warm and cool phases. And the warm phase is going to enhance the coastal marine productivity in Alaska. That makes some sense. If you're warmer, then Alaska, which is a cold place, will be more productive. But that inhibits productivity off the west coast of the contiguous United States. In other words, in the Pacific Northwest, Oregon and Washington, we're going to have less productivity during the warm phase. And the cold times are going to have the opposite. We're going to have more productivity in the contiguous United States and less productivity in Alaska. Let's look at that in that diagram. So there's the diagram. Here's the PDO. This is positive here. These are the negative PDOs. So warm phase, cold phase. During the warm phase, look at the productivity. Look how high these charts are. The warm phase is also colored in pink on this diagram. And we have pink and higher peaks here for the productivity of western Alaska sockeye salmon. There's more salmon during the warm phase, and also the Alaska pink salmon more during the warm phase. If you go farther south, in southeast Alaska, well, even there, it's more during the warm phase. But now come down to the Columbia River, and you see we're getting more Chinook in the cold phase. So it depends on the PDO, how our productivity is. So that's the Pacific Decadal Oscillation. More salmon in Alaska during the warm phase, more salmon in the Northwest during the cool phase. There's some of those. There's a Alaska sockeye salmon. Here is the Southeast Alaska pink salmon. And then here is a Pacific Northwest Chinook, spring Chinook salmon. And you can see the proud fishermen who caught those. I'd like to transition to ocean currents. We've already seen a little bit in connection with El Nino and La Nina. Let's look at this again. Okay, so ocean currents are influencing climate. We see here cold ocean currents along the west coasts of continents. Remember what we said, the trade winds are blowing the equatorial currents, the westerly winds are blowing these currents in the South Pacific and the North Pacific, in the North Atlantic and the South Atlantic. Those north and south, those currents are driven by the westerly winds. This is the west wind drift, named for the westerly winds that are pushing it. When the current hits the coast, it splits and goes north and south along the coast. Here we see a current hitting the coast here, and since it's heading towards the equator, it's a cold current. Here we see current hitting the coast here, and since it's heading towards the equator, it's a cold current. These cold currents create situations that lead to deserts along these coasts. So we've got west coast deserts. That's true here. We've got dry conditions. The Sahara is a very big desert. Dry conditions there. Here's the Namib Desert, which is also quite dry. The driest desert in the world is right here, the Atacama Desert. So these currents are creating different climates on the west coast, or desert climates on the west coasts of the continents. Australia, which is not shown in this picture, also has a cold current along its west coast, and that creates desert there. We have warm currents on the east coast, and that gives much more humid climates in those places. Here is a map of the climates in very simplified form of the Köppen-Geiger climate classification system, and you see just tropical versus dry versus warm temperate versus cool temperate, polar, and highland, and you can see that the dry is corresponding to the western sides of the continents, including Australia. See how those currents kind of fade in and show you the nature or the locations of where those cold currents are, making the deserts. Places that are warm temperate, those are going to be, and also tropical, those are going to be next to warm currents. So you've got tropical setting here and warm currents. Remember that warm currents are occurring where the water is near the equator or heading away from the equator. Near the equator or heading away from the equator. Now with equatorial upwelling, we looked at that when we talked about La Nina and also La Nada. So let's see what's causing that equatorial upwelling. Why is the water coming up along the equator? Well, it has to do with the trade winds. The trade winds are converging. It's called the ITCZ. Remember that? Intertropical Convergence Zone. That means the winds are coming towards each other. And it also has to do with something called Ekman transport. And we'll talk about what that is in a moment. But the basic idea here is that we have trade winds that are converging, but because of the Coriolis effect, the ocean currents don't go in the same direction as the winds. They actually turn to the right of the winds in the northern hemisphere at approximately 90 degrees if they could. They can't really achieve that usually, but they kind of try, if you want to emphasize that a little bit. Ekman transport in the northern hemisphere is to the right, Coriolis effect, and in the southern hemisphere is to the left. So if we take this trade wind here, it's a northeast trade wind heading towards the southwest, and we look at the Ekman transport, we see the Ekman transport is perpendicular to that, and that causes the ocean current to move towards the northwest or away from the southeast. And in the southern hemisphere, it would be mirror image, and you see now the ocean currents are moving away from the equator. Now, if the ocean currents are moving away from the equator, something has to come in to replace that water. And that's water from below. That's equatorial upwelling. Here's the Ekman spiral or Ekman transport. So we've got surface wind, and in the northern hemisphere, that surface wind blows it a little bit to the right in the northern hemisphere. This diagram is for the northern hemisphere. And then that water is pushing the water below it a little bit to the right. And that water is pushing the water below it a little to the right. You kind of get the pattern here. And a little to the right and a little to the right until you add them all up together, and it comes out being a net transport direction of average flow perpendicular to the wind direction. to the right in the northern hemisphere, to the left in the southern hemisphere. So wind-driven currents are at an angle to the surface wind because of the Coriolis effect. Here's the net transport. Wind direction, net transport of water. Perpendicular. Again, this one is for the northern hemisphere. It's turning to the right. So the net current direction is perpendicular to the wind, and that gives us equatorial upwelling, such as during La Nina and normal conditions. Trade winds converging, diverging ocean currents, causing equatorial upwelling.